from Utrecht University, and the title is Bianchi Identities for Non-Geometric Fluxes from Palatini-Lovelock-Cartan Gravity.
Okay, thank you. I would also like to thank the organizers for giving me the opportunity to speak here. This talk is based on a paper which was written in collaboration with Ralf Blumenhagen, Andreas Deese, and Felix Rennecke. Ralf is also here, already gave a talk, and Andreas will give a talk on Thursday, I think. This paper fits kind of in this whole discussion about non-geometric fluxes and non-commutativity and non-associativity. And closely related work to the paper I'm going to talk about appeared, for instance, here, and there are some further papers. And we already heard some talks about this by Ralf and Dieter and David and Peter just recently. All right, so the main question, well, let me first review roughly the setting. So what we heard already yesterday is that non-commutativity and non-associativity for the closed string can be characterized, for instance, by these expressions where the commutator of two closed string coordinates is giving in terms of the Q flux, and the cyclic double commutator of three closed string coordinates can be expressed in terms of the R flux. And this has been investigated in a series of papers which appeared during the last 2 years. Now, these non-geometric fluxes Q and R, which are appearing here, we've already seen this picture, can be obtained, for instance, by applying T-duality transformations. So, for instance, if we start with a usual H flux, which gives us a normal flux background on a flat torus, for instance, and if we apply one T-duality transformations, we arrive at something which one might call geometric flux, and the resulting space is something which people call a twisted torus. Now, as we heard already yesterday, we can apply a further T-duality transformation to arrive at something called Q flux, and the resulting space is called a T-fold, where not only different morphisms are needed to glue together patches, but also T-duality transformations. And then it has been argued that one can apply even a further T-duality transformation to arrive at an R flux, and these spaces are not even locally geometric anymore. Anyway, so this is roughly the setting, and it is clear that in order to understand non-commutativity and non-associativity, we might need a better understanding of these fluxes Q and R. And that is the purpose of this talk, or that was the purpose of this paper. Now, trying to find a better understanding of fluxes in gravity theories or in string theory, many people have done that, and this is all collected in these dots.
Sorry. Just make a slight complaint. You've mentioned generalized geometry and double field theory, and you've not mentioned Hull and Zweibach, any other papers by anyone else. I mean, you know, these guys, there's a whole group in Korea that have done double geometry.
Oh, you mean this?
And there's basically huge numbers of people, and you've not mentioned anyone other than your group. I mean, that's just a bit much.
Sorry, you mean this complaint here? This one? I'm sorry.
And all the ones before as well. I mean, you know, double geometry's got a long history, and there's been a whole bunch of people.
Here, or?
And then all of those, not a single mention of Hull and Zweibach. The whole group of Korea.
I'm sorry. I didn't want to neglect anyone. I just wanted to say that work which is closely related recently.
Closely related work appeared by.
I'm sorry. I didn't want to forget anyone. I'm sorry about that.
It's just, you know, there's groups of people who just don't happen to be here. Like there's a group at Imperial. There's all sorts of people involved, right? I mean, come on. Never mind. Get on.
I'm sorry about that. I wanted to point out a slightly different aspect of this work. What I was about to say is that there's a lot of work done, which I didn't cite here. What I wanted to cite is a paper work which we heard just an hour ago, which I wanted to point out here. And what I want to talk about is an even different approach to understand fluxes in gravity theories, based on the Palatini formalism. And that's what I'm going to talk about. So Palatini formalism is the approach where you treat the metric and the connection as an independent field. And so you would, for instance, write down such an action where you indeed treat this metric and the connection as an independent field. If you look at the field equations for the connection and you solve for these field equations, you find that the connection, that the metric should be, or that the connection should be metric compatible and that the torsion should be 0. So that means, starting from this action, you find the Levi-Civita connection. And if you look at the field equations for the metric, you find Einstein's equation. Now this is all well known. And what we now did was we wanted to incorporate fluxes into this framework. So what we did is we modified the Riemann or the Ricci tensor in this way. So we introduced another field, a three-form field, eta, and modified our expression in this way. And here T is the torsion tensor. And if you then go through this analysis, you see that now the metric still has to be compatible, the connection still has to be metric compatible, but it can have torsion, and this is what we wanted to achieve. And the field equations for the metric are modified into this way. Now, if you then integrate out the connection and just take this torsion tensor, take this solution, plug it in here, what you find is that your action looks like the normal Riemann tensor with the Levi-Civita connections, and there's a term looking like this. Now, to make a connection to string theory, it is if you want to make a connection to string theory or the string action, the NS and S sector for constant dilaton, it's done by basically identifying this eta with the H flux. And if you set this constant c squared to 1/12, you indeed find the string action for constant dilaton. And this is long been known. So basically what you can achieve, at least at linear order in the curvature, is that you can identify the H flux with the torsion. However, it has been shown that at higher orders in the curvature tensor, for instance, in second order, it has been shown that the H flux cannot be interpreted as torsion. And our main question at a technical level was to try to see whether we nevertheless can find some interpretation via the Palatini approach. And that's what I want to talk about. All right, so in order to look at higher order gravity actions, we considered the Lovelock action, which is shown to be consistent with the Palatini approach. It's given by this expression, where this is the determinant, and this is the usual Riemann tensor. And if you go through that, you can show that for k equals 1, you indeed find the Einstein-Palatini action, for k equals 2, the Gauss-Bonnet-Palatini action, and so on. And then, similar as we did before, to incorporate the fluxes, we changed our Riemann tensor in this way, which is very analogously of what we did before. Now, if you now go through the analysis at second order, well, first of all, the action at second order looks like this. What we do is we compute the field equations for the connection. We see, in order to solve that equation, we need to use this the first order solution, which we found earlier. And in order to find a proper solution, we also have to impose these restrictions on these fluxes. So the upshot is that if you do the second order analysis, we find some constraints on these fluxes eta. Now, then we looked again, can we make that compatible with string theory? But the answer is no, unfortunately. So in particular, even if you look at the Lovelock-Palatini action at second order with H-focused torsion, that's not compatible with the string theory action at second order in R. However, just as a side remark, then if we modify our Lovelock action this way, where we include these terms, then it can actually be made compatible. But that's just as a side remark. Since I'm running a bit late, let me just mention that at third under the curvature, the action looks like this, quite horrible. And then you compute again the equations of motion for the connection, and you try to solve that and show that this equation is satisfied. And you can do that by using, again, the first order solution. And actually, from the constraints on the fluxes I showed earlier, you find relation of this form which you actually have to employ, and that's a quite involved computation. Let me just mention that you can do that. We constructed this to be true for all orders, but in order to go on, let me now have a look at these constraints in a bit more detail. So the constraints I mentioned are these here, and sorry about that. And these constraints are a bit stronger than the constraints for the H flux we know. Sorry about that. Do we have some? No. No, well, it's fine. Just getting rid of that. Thanks. So what I should have done that before. Now, okay, what I wanted to say is that the constraints we found, these here, are stronger than the constraints you find from the usual Bianchi identities for the H flux. However, if you look at these constraints in particular, you can see that you can relate them to Bianchi identities for non-geometric fluxes, which were given, for instance, in these papers here. And furthermore, these constraints here actually precisely appeared for certain solution for exact string theory backgrounds, for instance, for Visser-Wiener-Mitten models. So basically our analysis where we wanted to, let me go to the summary slide. So our goal was to understand fluxes better in string theory, and what we knew is that at linear order in R, the H flux can indeed be interpreted as torsion, but at higher order this fails. And we wanted to understand that with the Palatini formalism, where we indeed managed to identify the fluxes torsion dynamically. But again, at second order, this interpretation again fails for the string theory action. However, we saw that for this Palatini formalism to make sense, we have to have new constraints on these fluxes, which can be interpreted as Bianchi identities. And this kind of got us onto the track for the next papers where we actually studied Bianchi identities for these non-geometric fluxes in more detail. And Rolf already talked about this, and Andreas will talk about this in more detail. Sorry for my voice, and thanks.
Some more questions or complaints? Okay, so not to thank Erik again.